Uh, in today's talk, our speaker is Lisa Flecker from Fairfield University. So feel free to begin wherever you want, Chris.
All right. Thanks a lot. Thank you very much for inviting me to speak today. I'm glad to meet all of you. I hope everybody can see and hear okay. So I'm going to talk about at most n-valued maps. This is a recent paper that I wrote with Dacilberto Gonçalves. He's at the University of São Paulo in Brazil, and Robert Skiba, who is at the Copernicus University in Torun, Poland. So let's get to it. Am I going here? Yes. So I have worked on several projects about n-valued maps, and this just means a function, a multi-valued function where the number of values always equals n, just for some fixed number n. You have one value in the domain maps to a set of exactly n different values. And they look something like this. So this is a 3-valued map of the circle. Most of my examples are going to be drawn using the circle as the domain. So the circle I'm thinking of as the interval with the endpoints identified. And this is continuous because the lines, when they leave the picture on the right end, they come back on the left end at the same point. So this picture, you have to consider the right hand. The right end is identified with the left end, and also the top and the bottom are identified. So this is a 3-valued map. That's because every point in the domain, if you look above, it has 3 y values. All right, S1 is the interval with the endpoints identified. So when I say n-valued, I mean exactly n-valued. Every point in the domain has exactly n values. All right. These we also call them equicardinal because the cardinality of the image is always the same number. All right. Now, in the paper that I want to tell you about today, this is about at most n-valued maps. They are ones that look something like this. So this is an example of at most 3-valued. It means for each x, the image set has at most 3 values. So in this example, like for most domain points, there are 3 values, 3 y values, but some of them have only 2. All right, and it's possible to have only 1, although in this case, I think there aren't any points with only 1. All right, it's like a 3-valued map, but you know the lines maybe cross each other sometimes. So the big question that we are addressing in this paper is just kind of like how should we think about these maps, and what are some techniques that we can use to analyze such maps. Now, my own point of view, or what got me interested in this, is fixed point theory. So you can do fixed point theory for multi-valued functions. If you have a multi-map x into itself, then we say x is a fixed point when x is an element of f of x. Usually for single-valued functions, you say x equals f of x, but for multi-valued, you have to say x is an element of f of x. That's called a fixed point. And a fixed point of a multi-valued function looks like this. You can think of, just like for single-valued functions, a fixed point represents an intersection of the graph of the function intersecting with the diagonal. All right. And you will notice for a equicardinal n-valued map, you can do the typical topological fixed point theory, which is like the Lefschetz number or the Nielsen number, the Nielsen fixed point theory. All of these things work for n-valued maps, and this was worked out by Helga Schirmer in the 80s, and then by Bob Brown later on. The reason that this works for n-valued maps is that locally near the fixed point, if you just zoom in near the fixed point, it just looks like a single-valued function. And so you can do all the same things, which is like you can talk about the fixed point index, the fixed point classes, and so on. Everything looks single-valued when you zoom in locally. All right? So that's what I just said. Fixed point index and fixed point classes, and all these things are well-behaved under homotopy of the n-valued map. All right? Everything is messed up, though, when you're talking about at most n-valued maps. So in this particular example that I drew, actually it's still true that locally every point, if you just look locally, it does look like a single-valued function. But if I change this by a homotopy, it can look like that. And now nothing works the way you want it to work anymore, because around that sort of It's like a double fixed point, but not in the typical sense of the fixed point index doubling up. So the usual constructions don't work for such a map, and this is why we need to be a little bit careful. So how do we handle at most n-valued maps? I'm interested in the fixed point theory, but the questions that we ask in this paper are just more general questions about n-valued maps, generally speaking. All right. And actually, this one here is fairly easy to handle. So there are some that are nice and some that are not so nice. This one happens to be fairly nice. I don't know if you can see why, but it's because it splits as a union of two single-valued maps like this, right? So the one on the top is actually the union of those two maps on the bottom, and those are just ordinary single-valued maps. So the it's at most 2 valued at the top. That one you can just address it by considering it as a union of two single-valued functions, and then you do ordinary things with the single-valued functions. So this one is fairly straightforward to deal with. All right. Some at most n-valued maps are easier to handle than others, and many other authors have noticed this. So in a lot of the papers about functions like this, these at most n values, they talk about like different classes or different extra hypotheses on their maps. And so we identified 5 different classes which have appeared in the literature. And most of these papers about these types of functions are not actually trying to address one another. So one paper will be about one of these classes, another will be about another of these classes, but they don't really talk about how these relate to one another. And that's mostly what our paper is about. So these are the name, we gave them these names. And so this talk, I just want to sort of talk about each of these different classes and how they relate to one another. All right, so the first one is what we call C. That is just general at most n-valued maps. This is all continuous at most n-valued maps. We should say a little bit about what this word continuous is supposed to mean here. There are actually 3 what I would say are obvious approaches to define continuity for an at most n-valued map like this. So the first one would be you can define continuity in terms of upper and lower semi-continuity, and this is a typical thing that's done for all multi-valued functions. You can talk about upper and lower semi-continuous, and this is basically if you take the classical topology definition of abstract, continuity from a topological space, that the preimage of an open set is open. When you're talking about a multi-valued function, actually the preimage is a little ambiguous. When f is a multi-valued function, there's actually 2 different ways that you could define what you mean by the preimage, and so this basic classical definition generalizes in multi-valued functions in 2 different ways. Then they're called upper semi-continuous and lower semi-continuous. Anyway, we consider only maps which are both of these. If you have one but not the other, there's some weird things that can happen that I don't want to get into. So this is the standard approach for defining continuity for an at most n-valued map. We say it's continuous if it's upper and also lower semi-continuous. All right. A second approach could be considering it as a map into a quotient space. This is more like a configuration space point of view. So if you have a map with at most n values, then you could consider this as a map into the Cartesian product y to the power n, because that would be n different points of y. And then you make a quotient by you quotient out where you consider 2 sets of endpoints to be equivalent if they represent the same set. And so you could also define continuity in terms of this being continuous as a map, as a single map into this quotient space. And then another way is you could use what they call the Hausdorff metric. So if y is a metric space, then there is a natural metric on the collection of all subsets from y, and that's called the Hausdorff metric. And so you can define an at most n-valued map as being continuous if it is continuous with respect to this Hausdorff metric. Anyway, we consider all these things in the paper, and in the paper we show that all 3 of these are equivalent as long as x and y are metric spaces. So from our point of view, we don't want to get into any very weird spaces, but at least as far as metric spaces go, any of these ways of defining continuity will work just as well as the others. All right. Okay, let's talk about these classes of maps. So the simplest one that we discussed is what we call U, and these are unions of equicardinal maps, and they're like the one that I showed before. So here's an example of, this is a at most 3 valued on the left there, but it breaks apart into a union of a single valued and then a 2 valued, all right? And so this is a union of equicardinal maps. And these ones are the kind of the most easiest to deal with. The first big question that we had, and I think the answer is not really obvious, can every at most n valued map split up in this way as a union of 2 equicardinal maps? We had to think about this for a little while, but the answer is no. There are some maps which can never be decomposed in this way into a union. And here's what I believe is the simplest counterexample. So this, again, is a map on the circle, and you can see there are at most 3 values. There's 3 in the middle, but only 2 values sort of on the 2 sides. And this function does not split apart as 3 single-valued maps. You might think, can I just break it apart like this? The bottom one, the top one, and then like one going across the middle. Maybe you can see actually this is not a valid decomposition because the last one there is not continuous as a map on the circle. Remember, because these are maps on the circle, where the graph leaves the picture on the right, it must come back at the same point on the left, and that one doesn't. So this actually cannot be decomposed in that way that I showed you, and we show in the paper that actually it's not possible to write this as a union of equicardinal maps. All right. So in the notations that we use in the paper, that means this class of the U class of unions of equicardinals is strictly smaller than C, which is the just all continuous at most n valued maps. All right. The next one in our bunch of classes of maps is what we call S, and these are symmetric product maps. Maybe you're familiar with this if you've symmetric products come up a lot in topology in general. But anyway, if I do have an at most n valued map, we can think of it as just a single map into the Cartesian product, because y to the n is just collections of n different points, and some of them are allowed to be equal. This is not quite the same as a set valued map, though, because if I'm just mapping into y to the power n, the values of this function will be ordered, ordered n tuples, and I don't want to consider the values with ordering, and so you can deal with this by doing a quotient. So we're going to take the quotient by the symmetric group, and this thing over here, this codomain y to the n modulo the symmetric group, that's called the n-fold symmetric product. So it represents n tuples of elements from y, but you consider them as being unordered. All right. It's just like y to the n, but the points are considered as unordered, and they can have repeated elements. All right. So we can view, if you have a single map from X into the symmetric product, we can think of this as a multi-map where the image of each point is an unordered set of n or fewer elements. So that means it looks like an at most n valued map. So this class S is all of the maps into this space SPn of y. And all of those things, we can consider them as at most n valued maps. The natural question here is also, are these the same? Is it the same thing that I'm talking about? One of these symmetric product maps, is that just the same as mapping into just any continuous map? Actually, they are not quite the same. They are not equal. And here's a counterexample. This one again is a counterexample. This one is at most 3 valued, but actually it turns out you cannot express this as a map into the threefold symmetric product, and I will tell you why. Remember, this threefold symmetric product looks like triples considered without order, all right? And if you just look at the picture here, if you think of this as mapping into SP3, the picture is actually ambiguous. That's because, for example, what is f of 0? That would be the leftmost point. On the picture, I can see 2 values there, but actually, if you are thinking of this as a map into SP3, those 2 values, that could represent the 3, the triple 0, 0, and a half, or it could represent 0, a half, and a half. And you can't tell the difference by looking at the picture. I only see 2 points there, which means in the symmetric product, either the bottom one is kind of double or the top one is double. And when you look at the picture, you can't tell the difference, right? But actually, this picture, if you look in the middle, it is unambiguous. There's no problem in the middle. There are 3 values right there. But consider what happens if I sort of start in your mind looking at those 3 values and just move to the right continually. If you follow the graph all the way to the right, end, you'll see that the 2 values up top will come together, and then we're going to have only 1 value in the bottom and 2 on the top. So actually, the picture, I said before the picture was ambiguous, but in fact it's not really, because if you start in the middle and move to the right, you can see the value f of 1. It must be 2 on top and 1 on the bottom, all right? But maybe you can see where the problem is. If we also follow the point in the middle all the way to the left side, then for the same reasons, there will be 2 points on the bottom and 1 on the top. So we can see that f of 0 must be 2 on the bottom and 1 on the top. But this is a problem. This is not going to be continuous, because I said f of 1 is something, but f of 0 is something different. And remember, if this is supposed to be continuous on the circle, the value on the right side has to be the same as the value on the left side. So that means this thing, it is a set-valued map with the most 3 values, but it's not a continuous map into the threefold symmetric product. All right. So that means this class, the symmetric products, is a proper subset of the class of all continuous functions. All right. What about comparing this S class and the U class? So this would be all symmetric product maps versus the unions of equicardinals. Are those the same class? Actually, when I first started thinking about this, I thought that they were equal, and it was my goal to prove that these 2 sets of functions are equal, but actually they're not equal. The U is a strict subset of the S class. It's not so hard to see that the U is a subset. If you start with a map which is a union of equicardinals, then you can write, your map F breaks down into a bunch of individual equicardinal maps, and then you can just sort of bundle those maps together, and it will be continuous as a map into SPN. You have to check that the continuity is actually satisfied, but it really is. So if you do have a map which breaks apart as a union, then you can package up that union and make it a map into the symmetric product. So that means this U class is a subset of S. And in fact, the U class is strictly smaller than S. That is to say, there are some symmetric product maps which are not actually a union of equicardinals. And this is a slightly weird example, but not too weird, I guess. So here, the domain, I am considering there's like an interval in the middle, which is a normal interval, but then the interval on the right side and the interval on the left side are having their ends identified. So it looks like 2 circles. The domain looks like 2 circles with an interval connecting them in the middle. And it turns out this one, it is a map into the twofold symmetric product, but you cannot write it as a union of equicardinals. You can tell, so first of all, it's not exactly 2-valued by itself. So if you want to break it into a union, it would have to be a 1-valued union with a 1-valued. But you can tell that's not going to be possible because of the two parts on the ends look like those are 2-valued functions that cannot be split into single-valued functions because of the continuity condition for those circles. So this is an example of something which is in the class of S, but not in U. All right. So far what I've said is this: we have a nice kind of containment here. The U, that's the unions of equicardinal maps. Those are kind of like the smallest class and the most well-behaved, and then we have a larger class of this S thing, and then the most general class would be the C one. All right. I got two more classes. So one is this thing called W, and this is something that actually a little behind the scenes, Dasseberg and I sort of started working on this project for many months before Robert joined. Dasseberg and I had not ever, well, I think also Dasseberg, but I had never heard of weighted maps, but Robert is sort of an expert in this thing, weighted maps. I'm going to talk only about weighted maps with weights in N. But anyway, they look like this. We call this an N-weighted map. It's a multi-valued map where there's some additional structure, and that is that each individual value has a natural number associated to it, which is non-zero. So, and those numbers are called the weights. So this is an example of a weighted map on the circle, and every part of the graph has these weights on it. And so individual points, in this case, can either be weighted with a 1 or a 2. The weights have to be assigned continuously, which means that integer number has to be constant on those arcs for it to be continuous. And they add up at intersections. So you can see sort of the red lines here are all weighted 1, and whenever two 1s come together, they add up to a 2, and then the 2 can split apart into 2 1s later on. All right, this is a very natural kind of thing. This is called a weighted map. We call them n-weighted, so we're only considering weighted maps with positive integer weights. More generally, there's a theory for weighted maps where the weights come from any ring, but we didn't get into that generality. All right. So anyway, what kinds? The question is, like, what kinds of maps can you actually put those numbers on, right? And it's not always obvious how to assign those numbers. Like in this example, can you tell me how you should assign those numbers so that all of these continuity conditions work out? Like the numbers have to add up when the arcs meet. Actually, in this case, it is possible to do that. There, I did it. But this is not so hard to do, but it's not obvious when you're looking. Like if I didn't show you those numbers, could I just point to a part of that graph and ask you, like, is this going to be a 1 or a 2 or a 3? It's a little complicated, right? Some of them are 1s, and some of them have to be 2s, and some of them have to be 3s. So it's not obvious always how you could assign those numbers. And it's not even obvious that it's always possible to assign the weights in a coherent way. So the immediate question we had is, can you always, like for every map, can you always assign weights in this way? All right. Here's a strange one. This example I would like to consider as only on the interval, not on the circle. So this one is, when you look at it, you will see it's at most 3 valued. But if you try to draw the weights on it, it has so many branching paths there. Actually, the weights that you draw, you have to go up to a weight of 3 and 1. So, like if you look on the left end, you will see a point at the bottom of weight 3 and a point at the top of weight 4. So actually, there's a weight 3 point at the bottom and a weight 1 point at the bottom. So the total weight here is actually 4, and it's not possible to make the total weight be 3, even though this function only has 3 different values at every point. All right. This one is at most 3 valued, but the weights that you have to use actually kind of go up to 4. And I will just point out this picture, I said I'm not considering this on the circle because this picture is not legal on the circle because the weights are supposed to be continuous, and the weights do not match up when you go around the circle in this particular example. All right. And maybe you can see actually sort of this is what I just said. If you assign the weights, the total weight sum in this example is 4, even though there are only 3 values. So this is a little strange. If you try to do this same old example, this is kind of like our standard counterexample. On the circle, you have a serious problem here. If you tried to assign the weights, let's imagine that we just assigned the weights in some way. Because the circle wraps around, all the weights on the bottom, sort of the line across the bottom, has to be all the same weights, and the line across the top has to be all the same weights. Where A, B, and C here, the diagonal line can have some other weight. These are all non-zero positive integers. But you can tell actually there's a problem here. Because they're supposed to add it up, if you look at the intersection point on the top, you would require that C plus B equals C again, and that's not possible. So this map cannot be a weighted map, all right? There are some examples where there's just no way to assign the weights. And what do we need for the weights to be possible? Like this one, it is possible to assign the weights, but in some examples it is not possible. Really, I would say on an intuitive level, what you need is there has to be some way to decide coherently which points is like a single point versus a double point versus a triple point. So when I worked this one out, I had to look carefully at the branching and say, I know this part has to be a 2 because later on it's going to split apart into 2 individual ones or something like that. You have to go through the picture and decide for every point which one of these points is just like a single point versus a double point versus a triple point. All right. Maybe this sounds familiar. If you think back, about 15 minutes, this is actually the exact same question I was asking about the symmetric product maps. When you look at the graph is this one like 2 points on the bottom and 1 on the top, or is it 1 point on the bottom and 2 on the top? Actually, these two questions are the same question. Is it possible to coherently decide if there's like 1 over here and 2 over here versus the other way around? It turns out that the continuity of the weights in a weighted map is an equivalent condition to the continuity as a map into the symmetric product space. All right. So, and in the paper, I'm just giving the idea here, but in the paper we have all the details. We show that these two categories, or these two classes of maps, the symmetric products and the weighted maps, they are the same class. And this was a nice result. I mean, there are several papers about symmetric product maps in fixed point theory, and also several papers about weighted maps in fixed point theory. But I guess it was not realized that these are actually kind of the same class, which I thought was a nice result. All right. Okay, so this is what we got so far. All right. I have just one more. I hope you're not getting bored with all of these different classes. One more class of Atmos n-valued maps that we considered in the paper, and that is what we call the n-fold maps. And these were defined by Michael Crabb starting in 2015. Actually, unfortunately, Crabb called these, he just called them n-valued maps, which was the same word that Bob Brown had used and Helga Schirmer had used for exactly n-valued maps, which is not what Crabb meant. So we, in this paper, we refer to them as n-fold maps, just so that they are distinguished from the other ones. And an n-fold map is constructed using covering spaces. So the idea is, if you want an n-fold map from X into Y, you begin by taking an n-fold covering, a finite covering of the domain, and then you choose a single valued map from that covering space into Y. So the idea is this finite cover, this X bar, is, you think of it as like, it's the same as X, but every point has been sort of duplicated n times, all right? So X bar looks like n copies of X. Now, it's a covering space, so it may not be like a disjoint union, but it sort of topologically is like taking n different copies of X, and then you choose a single valued map from X bar into Y, and this is just like mapping n different points, all right? That's the basic idea. And then you define F is going to be your multi-valued map, and it's defined by doing P inverse first and then this F bar. So P inverse of X takes X into n different values, and then you map all each of those n values by the single valued map F bar, and you obtain a function of with n values. Although, because of the way that F bar is chosen, those n values, some of them may equal each other. So really you get an at most n valued map when you do this. This is Crabb's n-fold maps. And Crabb defined Lefschetz number and all kinds of Nielsen theory for n-fold maps in some papers that he wrote. All right. I will say at this point, it's sort of obvious that these unions of equicardinals are all realizable as n-fold maps. If you have a union of equicardinal maps, it's not so hard to turn this into a sort of like a disjoint finite cover. And it's also not so hard to show that an n-fold map is automatically corresponds to a map into the symmetric product. I don't want to get into the details of that too much right now, but and so this class F is kind of in between the U and the S class. All right. Again, when this project began, I had thought that these were all the same thing, but it turns out they're not. So we actually show that these are proper subsets. That means the U and the F and the S, they are all actually different classes of maps. And so this is kind of the last thing I'm going to say is just why should you believe that these are really proper subsets? So first of all, the U is not the same as the F. That means there is an n-fold map which cannot be written as a union of equicardinal maps. So in particular, we have a counterexample. So our example is a two-fold map from RP2 to S2, which cannot be written as a union of two single-valued maps. And this map is constructed like so. It's not so hard. You take the you have to begin with a finite cover, and so with RP2 we take the usual sort of two-fold cover of RP2 by the two-sphere. And then the map that we choose, S2 to S2, is going to be this one here. F bar of XYZ is XYZ x, y, and the absolute value of z. So thinking of the sphere in 3 coordinates, you're just pushing everything into the top hemisphere and keeping the points where they are otherwise. All right. So this defines a two-fold map if we do it this way. So you start with a point in RP2, you bring it back to 2 points on the sphere S2, and then you push them up into the top hemisphere. All right. If you do this starting from the point 0, 0, 1, then you only get one value because when you pull that back into S2, you get basically the North Pole and the South Pole, and then you push them up and you get only one value. So this F that I'm talking about is not exactly two valued. It is also not a union of one values, and that's because if you think about, there's some details here, but if you think about this map restricted to the equator, what you get is I'm writing this now as if these were in the complex plane. What you get is this map, e to the I theta comma e to the minus I theta, and that does not split as a union of two single-valued functions. All right. So all this means this map that I'm describing is a twofold map, but it's not a union of equicardinals. So that means that the U and the F are not the same class. All right. And then what about the F and the S? This is a much weirder example, but it turns out there is a at most two-valued map from the 5 sphere to the 2 sphere. And this map is a symmetric product map, but it is not a twofold map. And so the way we demonstrate this is we are going to count homotopy classes. This is really the only time in the paper when we use homotopies, but we're going to count the homotopy classes and use some well-known facts. I put that in quotes because these facts are not especially well-known to me, but they are well-known facts that you can look them up. Anyway, if you want to count the symmetric product maps, then I'm writing those brackets as the homotopy classes. I want to count the maps from S5 into the twofold symmetric product of S2. So I'm looking for homotopy classes from S5 into SP2 of S2. All right. First well-known fact, that's WKF. The first well-known fact is somebody has determined SPN of S2 is homeomorphic as a topological space to the CPN, the complex projective plane. All right, so that means the homotopy class I'm trying to count is the same as the homotopy classes of S5 into CP2. This, of course, is the same as pi 5, the homotopy group, pi 5 of CP2, and this also is a well-known thing that somebody has computed. A well-known fact that this is the integers. All right, so considering symmetric product maps, there are infinitely many homotopy classes of symmetric product maps, S5 into S2. All right, I'm going to do similar things to count the n-fold maps. So now let's count the two-fold maps, S5 into S2. These ones, remember, they are constructed by first you choose a finite cover, and it's going to be a two-fold cover this time. So we choose a two-fold covering space of the domain. The domain is S5, which is simply connected, so the only two-fold covering space is this. It must be just the disjoint union of two S5s. And then we need to choose a single-valued map from this disjoint union, S5 union S5, into S2. All right? So we're going to count homotopy classes like that. And again, by some standard facts, kind of off-the-shelf theorems, we can count these. This is just how homotopy classes work for a disjoint union domain. The number of homotopy classes or the set of homotopy classes is this product, S5 and S2. Those S5 and S2, those are homotopy groups, pi 5 of S2, and those also, by some well-known facts, they are each equal to the integers mod 2. All right, and so there are 4 homotopy classes of twofold maps. Remember what I said before? 4 homotopy classes of twofold maps, but there are infinitely many homotopy classes of symmetric product maps. And so they are not the same class, and there are more symmetric product maps. That means some of these symmetric product maps are not expressible as twofold maps. All right, so the F is a proper subcategory of the S. All right. So anyway, this is the main result, which you can see in the paper, but it's expressed in this way. So all of these classes have appeared in various papers, and in fact, all of them have been considered in fixed point theory for multivalued functions. and now we've demonstrated that they kind of exist in this hierarchy. All right. Just to a couple more technical results. We also give some in the paper some conditions on X and Y, which make the class U equal to the class W. So under certain conditions on X and Y, actually all of these classes are the same. When I said above that they are not the same, what I mean is there are certain choices of spaces where you can find sort of maps in one class but not the other. But for some spaces, they all turn out to be the same. All right. And then we also, in a sort of a configuration space point of view, we also calculate the homotopy groups for this thing which I'm writing Cn of S1. That's the configuration space of at most, or the configuration space of sets of at most endpoints in S1. So we talk about that a little bit. All right, anyway, I think that'll do it. Thank you very much for your attention.
Thank you very much for your talk, Chris. So now we open the round of questions. So any questions? Any? Let's check the people connected.
But I have one question in relation with your paper. When you define the weight index, this definition seems to me very similar to the Lenz's number, in the sense that we could consider the summatory of the omega xy as the summatory, an example of omega could be the fixed point index. And it agrees with the second part of the definition of a n-weight map. That is that the conditions of locally, that the sum is locally equal, disagree with the additivity property of the index. So for example, if you consider a map from X to the maps from Y to Y, then you could, I think that you could define omega xy as the index of x fixed point of f of x. With this, I think that we obtain a proof of the homotopical invariance axiom of the fixed point index. And my question is, are there any results with this weight index that are potentially interesting in fixed point theory?
Yeah, this is an interesting question, and I have not thought about this before. Like I said, I'm not. I have only recently learned about weighted maps, but yeah, I agree that the conditions for the weights is similar to the homotopy and additivity properties of the index, and yeah, I'm sure you're aware. Like there are uniqueness theorems that say that the fixed point index is the only function which can satisfy these kinds of additivity and homotopy properties. Yeah, this is an interesting question, and I don't know if there are any results to that effect. It's a good question. Sorry, I can't say.
Any other questions? Or questions? Okay, then we thank Chris again.
All right, thanks.
Okay, it has been a pleasure to have you here, Chris.
Yeah, my pleasure too.